तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Yeah, so let us go on to the problem of a particle in a 1D box. Okay. This is a free particle which is moving back and forth in a one dimensional box, and if you recall, classically if I plot x versus p, the phase trajectories are just little rectangles, sides of rectangles. This is minus 2m e, this is root 2m e, that is 0, this region is forbidden, that region is forbidden, and this is L along the x axis. Okay. And then the original Bohr quantization gave us a set of discrete energy levels, and these energy levels were given by En is n squared h squared over 8m L squared, which I prefer to write as n squared pi squared h cross squared over 2m L squared. H cross is h over 2 pi. Okay. So this gave us a set of quantized energy levels, but now let us solve the Schrodinger equation and find out what the actual true energy levels are. I would expect the result that we get to merge with this result for sufficiently large n when n becomes much greater than 1, but it will turn out that it is actually true for all n 1, 2, 3, 4 and so on. So what is the Schrodinger equation? Well, for the energy eigenstates, the time independent Schrodinger equation is minus h cross squared over 2m, and then a del squared, but since we are talking about one dimension, that just becomes d2 over dx2 plus v of x, the whole thing acting on phi of x equal to En phi n of En phi n of x. That was the time independent Schrodinger equation, and now let us look at v of x is 0 inside the box, it is infinite outside the box. So let us look at what happens inside the box, 0 less than x less than L inside the box. We have d2 over dx2, that this term, that term is 0, and then I could move this to the other side and bring this back here, plus kn squared phi n of x equal to 0, where kn squared is let's is equal to 2m En over h cross squared. Okay. So I take the minus sign there and then bring it back here, so it is a plus sign, and that's what the equation is. Okay. And the solutions to this are trivial. This is just a simple harmonic equation, and therefore phi n of x is something of the form a cos kn x plus b sin kn x. That is the general solution. Notice that we should write down the general solution. So it is a superposition of all possible independent solutions, linearly independent solutions. There are two of them, just the oscillator equation, this is what you get here. Okay. And now we have to impose boundary conditions. And what are the boundary conditions we should impose at 0 and L? it should be continuous. That is not sufficient, that it should be continuous. You need to say what it is at the boundaries. It should be 0 at the boundaries, because it is an infinite barrier. The probability of finding the particle outside the box is 0. So at the boundaries, the condition you impose are phi n of x, phi n of 0 is 0 is phi n of L. This is going to determine the spectrum. Had we changed this to some other boundary conditions, you would get another spectrum. And of course, we put at 0 x equal to 0, this thing goes away, and then you want this to be 0, and if you put x equal to 0 here, this is 1, so it says a equal to 0 right away. This portion goes away and you are left with just that thing there. But imposing the other boundary condition says that sin k n L equal to 0. Unless b is also identically 0, but if b is 0, then you can't normalize the solution, because we would like to have also the normalization condition 0 to L dx b squared sin squared k n x to be equal to 1, because you want the total probability of finding the particle inside the box to be equal to unity at all times. So that says that sin k n L equal to 0, which implies that k n equal to n pi over. Therefore, if you put this in, you immediately get the E n to be equal to h cross squared times k n squared is n squared pi squared over 2m L squared. So indeed these are the exact energy levels, which we got also by this Bohr quantization rule. Now in this particular problem, the problem is so simple that the Bohr rule actually gives the exact answers, because there is no potential inside and it is infinite outside. So it is not quite an accident, there are reasons why this should be so, but we will see this later on. But to other problems, why in this particular instance the Bohr quantization rule actually gave the exact eigenvalues. What are the values of what are the wave functions? Corresponding to this, you have phi n of x, and that is equal to b times sin n pi x over L, but this b should be normalized by this rule here, and please notice that this wave function is arbitrary up to a phase factor, because all that happens, the normalization only fixes modulus phi n squared of x up to a constant. So it fixes mod b squared, and b could be a complex number with a phase factor, and that is not showing up in this wave function at all. It is actually irrelevant, because as we will see for all physical quantities the phase factor multiplying the normalization is irrelevant. Choosing that to be real, this phi n of x turns out to be 2 over L sin n pi x over L. And what are the allowed values of n? Is it 0, 1, 2, 3, 4 or 1, 2, 3, 4? Well, as it stood, n was just an integer here. Why do I choose only the positive integers? It does not matter, because sin n pi x over L is minus sin minus n pi x over L. So if n were negative, you would get the same wave function over again with just a multiplicative factor. So it is not linearly independent. There is just one linearly independent solution for each value of n, and notice the energies are actually proportional to n squared. So it really does not matter whether n is positive or negative, which is a reflection of the fact that sin this guy and minus sin this guy are linearly dependent on each other, just multiplying by a constant. So you may as well choose just positive integers. Why not 0? Why not 0? Yeah, then the wave function would vanish everywhere, and if it vanishes everywhere, then it can't be normalized to unity. So therefore the allowed values are just n equal to 1, 2, 3, etc., all the way to infinity. What are the actual wave functions corresponding to this? Well, you can also ask what is phi n of x comma t, what is that equal to? So what is the time dependent eigenstate equal to? Yeah, it is just e power minus I e n t over h cross phi n of x. So that too is nothing new, it has just got this phase factor multiplying it, that is it. So this specifies completely the state of an energy eigenstate or the Hamiltonian eigenstate for this particle in a box problem. Now I have several questions to ask. Are the energy levels degenerate or non-degenerate? Is there a unique state associated with each energy level, or is there more than one state associated with it? It is unique, there is no degeneracy in this problem. This is typical of one dimensional problems, there is no degeneracy, and the reason is rather deep. Degeneracy is a reflection of symmetry in the problem, in general continuous symmetry, and there is no continuous symmetry in this problem at all. Later when we look at 3-dimensional problems, then you would have rotational symmetry, it is a continuous symmetry, and associated with it you would have a degeneracy, because the system would be invariant under rotations of the coordinate axes. In one dimension there is no question of any rotation at all, there is no symmetry in this problem at all of this kind. Okay. The second question, why does not Planck's constant appear anywhere in this wave function? After all it is a quantum problem, why does not Planck's constant appear anywhere? It is purely dimensional reasons. What are the parameters in the problem? What are the constants in this problem? No, the energy is not a constant in this problem, no, the energy changes, depends on what state you are in. What are the parameters? Yeah, L certainly, what else? M. There any other constants in the problem? There is one more constant, it is sitting everywhere. Pardon me? No, where is in that, where is the constant? Where? There is no energy scale associated with the potential. Had this been a potential of depth V naught or something like that, I would say V naught is a constant, that would have a dimensional constant, dimensions energy. What else? H cross, definitely Planck's constant is sitting there. Anything else? Anything else? How about the speed of light? Why does not the speed of light appear here? It is non-relativistic. How about Newton's gravitational constant? Yeah, you have said it is not, it is in flat space, no gravitational constant, no gravity is included. How about Boltzmann's constant? You are working at absolute zero, it is not in contact with the heat bath or anything like that. Had you put it in contact with the heat bath, then yes. So there is no relativity, so C is absent, there is no gravitation, so capital G is absent, you are working at t equal to 0 and therefore K Boltzmann is absent. The only constant that can appear here is Planck's constant. So everything that you do, you have to play with just these 3 constants here. Now what are the physical dimensions of this wave function? What are the physical dimensions of phi n? What are the physical? We want this condition, we want guarantees by the way that integral 0 to I have not completed the solution, sorry. What is the wave function outside the box? It is 0, so we better be careful, we better write this properly, we better write this as equal to root 2 over L sine n pi x over L, 0 less than equal to x less than equal to L, 0 x less than 0 and x greater than L. So let us be careful, that is the exact solution. Now the normalization constant of course says minus infinity to infinity dx phi n of x whole squared equal to 1. And of course the integral is only from 0 to L because phi n of x is identically 0 outside the box. So what does this imply for the physical dimensions of phi n of x? L to the power minus half, so this must be 1 over square root of length, because this is a length and when you square it this must be equal to a probability which is 1. Now is there a parameter of dimensions length in the problem? Yes indeed, capital L, so it is not surprising that it appears here. Why does not Planck's constant appear anywhere inside here? The argument of the sign cannot have dimensions because the sign is a power series going all the way to infinity, therefore whatever the sign of anything cannot be dimensional, that thing can't have dimensions and it must depend on x. So you have an x and that must be compensated for by an L. You could say what about multiplying it, n pi are dimensionless, what about some other constants? Well if you have any Planck's constant appearing there is a time that appears in the problem and there is no other parameter of time or with dimensions time involved in it to cancel that. So that is why it never appears. This is the reason why Planck's constant does not appear in the wave function, it can't for dimensional reasons. If you look at the hydrogen atom problem then Planck's constant would appear even in the wave function. Where does it appear in the wave function? Where does it appear? What does the ground state of the hydrogen atom look like? What does the wave function look like? It is spherically symmetrical, so it goes like e to the minus the distance e to the minus r, but it can't go precisely like e to the minus r, there must be something else which compensates it, or divided by some length, there must be some natural length in the problem. What is that length? Yeah, 4 is not important but it is a naught is important, a naught is the Bohr radius. So a quantity of dimension length is formed automatically, but the hydrogen atom is not inside a box. Where does this a naught come from? What is it made of? Yeah, it is the average distance and so on, but this a naught must come from some fundamental constants. It can't come from r is already sitting there. So it must come from the parameters in the problem. What are the parameters in the hydrogen atom problem? What are the analogues of L, M and H? What are? Well yes, definitely the charge of the electron plays a role. What about its mass? Yeah, the mass will play a role. What about Planck's constant? Yes, because it is quantum. Anything else? Anything else? You got a Coulomb interaction there. Yeah, permittivity, I do not like to say permittivity because that is a matter of units, the speed of light in vacuum, that is the fundamental thing. Even though it is non-relativistic, as soon as you have electricity and magnetism the speed of light is going to play a role. So C would definitely play a role. So you see the time here can be cancelled by the time there and so on. In fact it appears always as CH cross because the T inverse in C is cancelled by the T sitting here always, so that is the way things work. And then the mass, the charge and so on and so forth. So from these quantities, anything else? Is there any other constant we have left out? How about Boltzmann's constant? No, you are at t equal to 0. How about gravitational constant? No gravity, yeah. So this is it, this is it. From these quantities you can form a quantity of dimensions length and that will play a role and that is what a naught is. So that is where it comes from. So therefore Planck's constant does appear in the wave function, it generally does, but in this particular problem the particle in a one dimensional box there is not another dimensionful parameter with time involved in it and that is the reason why it can't appear in the wave function. So purely from dimensional considerations this is all it is. Okay. Now that we have the wave function in place we can write down what a general state is going to be, it is just going to be a superposition of all these guys. So that becomes a trivial matter. But now let us ask, in one of these energy eigenstates let us ask some serious questions. First of all, is this a momentum eigenstate or not? Is this a momentum eigenstate? If it were a momentum eigenstate, then it must obey the following rule: momentum operator acting on the wave function must give you number times wave function. It means the momentum operator P acting on phi n of x must give you the eigenvalue corresponding to the momentum, eigenvalue times phi n of x. That is clear, a real eigenvalue is what it must give. Now what is the momentum operator represented by? What is it represented by? Minus IH cross d over dx phi n of x, and the question is this equal to number times phi n of x? Is this true? Well, you have phi n of x sitting there, it is a sine function. What happens if you differentiate it? So is it an eigenstate? No, it is definitely not a momentum eigenstate, but please answer for me the following question: this is a free particle, there is no potential, so the Hamiltonian is just p squared over 2m. Which would imply that the Hamiltonian commutes with p. This would imply that the Hamiltonian commutes with p, and then eigenstates of one are eigenstates of the other. But we just found out that we are not, the energy eigenstates are not momentum eigenstates. What is the resolution to the paradox? P commutes with p squared. P commutes with p squared, so this is definitely 0. If H is equal to this is definitely true, but we just discovered that those states are not momentum eigenstates. Pardon me? It is okay, real eigenvalues. So the paradox is the following, the question is the following: it appears as if the Hamiltonian in this problem is just the kinetic energy, it is a free particle, commutes with the momentum operator because p commutes with p squared, and yet the energy eigenstates, the eigenstates of the Hamiltonian are not momentum eigenstates. Why is that? So somewhere I made a wrong statement. Pardon me? It is not completely free, not true, it is not true, very good, it is not true. This has a V of x sitting here. It so happens this is 0 inside, infinite outside, and I just said it is a free particle very quickly. It is not free, it is sitting inside the box. And then of course this is not true because this does not commute with that. So energy eigenstates are not momentum eigenstates necessarily, unless the Hamiltonian is truly a function only of the momentum. It is not. It says this V of x definitely is 0 for x between 0 and L and infinite for all other values of x, so it is not a constant. So be careful when you read texts which say a free particle inside a box. It is really, you must take it with a pinch of salt. It is free inside the box, but it is not a free particle in the real sense of the word. So that is the reason why these are not momentum eigenstates. On the other hand, what would momentum eigenstates actually look like? What would a momentum eigenstate look like? I asked the following question. So let us say P on some state chi of x equal to eigenfunction times chi of x. So number P times chi of x. This would imply minus IH cross d chi over dx equal to P chi. And you can write this down as P over H IP. This would mean chi of x is proportional to e to the I P x over H cross. Do you agree? do you agree that momentum eigenstates must look like e to the power ipx in the position basis? We saw that earlier. So does this remind you of a momentum eigenstate? Does this remind you of a momentum eigenstate or a superposition of momentum eigenstates? How many of them are there? Why do you say that? Yeah, so I can write the sign I theta, sin theta can be written as e to the I theta plus e to the minus I theta. So I can certainly write this phi n of x as root 2 over L 1 over 2 I times e to the power I k n x plus e to the minus I k n x, where k n minus. So does it remind you of something? What are the momentum eigenvalues? H cross kn. So H cross kn is giving you the momentum eigenvalues. One of them would be going like this, the other going backwards. Remember, this particle is bouncing back and forth. So classically its momentum would have two values. Every time it is moving forward it has a value square root of 2me, and when it is moving backwards it has a value minus square root of 2me. Quantum mechanically the eigenfunctions of the Hamiltonian are indeed a superposition of two apparently momentum eigenstates, one corresponding to this motion and the other corresponding to this motion. Agreed? Does everyone agree? So what does the momentum space eigenfunction look like? What does the momentum space wave function look like? I did not solve this problem in the momentum basis, but we could do that as well. What would the momentum space wave function look like? So what would phi n tilde of p look like? What would this be? It would be a superposition of two momentum eigenstates, one of which has the momentum h cross kn and the other is minus h cross kn. So when you have two such things, what does the distribution look like? Two sharp values of the momentum. So what would it look like? I mean, I can sit down and compute the Fourier transform of phi n of x and the job is done, but we are trying to guess the answer backwards, right. So here is minus h cross kn and here is plus h cross kn, and you are told it is not a momentum eigenstate. If it were an eigenstate it would be just a delta function at that point, but it is a superposition of two eigenstates. So what does the wave function look like? It would have sharp peaks at what points? Plus or minus h cross kn. So what should I draw? A delta function here and a delta function here. That is what this function looks like, right? Two momentum eigenstates. Classically we can understand this. It is because the fellow is either going this way or going that way. That is the end of it. So the important lesson is, because it is not a free particle, because the momentum does not commute to the Hamiltonian, Hamiltonian's eigenstate is not an eigenstate of the momentum in general, but each eigenstate can be written as a superposition of two plane waves, and it looks like the superposition of two momentum eigenstates, which is perfectly consistent with the classical picture. Everyone agrees? Yes? But you see, quantum mechanics is a very tricky subject. So what we should do is to check this out and see if it is really true or not. Really, it worries me and it should worry you too. Why should it worry you? I already proved, is the wave function square integrable? the wave function is square integrable, right, it is in L2, phi n of x is a member of L2, but we just proved a theorem that if phi n of x is in L2, phi n tilde of p should also be in L2, right. What do you do with something which has delta functions? Is it square integrable? Is a delta function square integrable? No, it can't be squared. So it really is worrisome. This is not true. This is not true. The only way to settle this problem is actually to find the Fourier transform of this guy and see what it does. So let us do that. Let us do that. Phi n tilde of p is integral minus infinity to infinity dx phi n of x multiplied by a phase factor which was the overlap function between x and p. So it was e to the I p x over h cross. Was it plus or minus? I do not remember the convention I used. Plus, it was plus. You should check that out. We can go back 3 steps and do it, but okay, apart from a sign, this is what it is. It's plus. Now what is that reduced to? You agree this is the Fourier transform? No question about it. What should I write next? What should I write next? I should substitute this. I should put this in, and when I do that, what happens to the integral? It becomes 0 to L. Had it not been that, so had this been integral dx e to the I px over h cross and then a 2i e to the I kn x minus e to the minus I kn x and a root 2 over L. Had this been minus infinity to infinity, then each of these guys gives you a delta function at p equal to plus or minus h cross kn. But unfortunately or fortunately for us, it is 0 to L and they are not delta functions. Okay. Pardon me? That really does not matter at all. So these are not delta functions. E to the I kx integrated over x from minus infinity to infinity is delta of k, but if you integrate over a finite range it is not true. That is why I was careful to write the wave function as this sine function inside, 0 outside, 0 outside. So this wave function really looks like this. For instance, the n equal to 0, n equal to 1 case, that is a sine function that does this, and then it is 0 outside, it is 0 everywhere outside. The function is continuous at these points, the slope is discontinuous. So the second derivative of the wave function would have an infinite discontinuity at these two endpoints. The curvature is very different, the slopes are not continuous at all, this slope and this slope are different. So the curvature undergoes an infinite discontinuity, and indeed you see that the wave function must satisfy phi n double prime plus kn squared phi n plus v of x phi n equal to 0. Really it satisfies that, but v of x has an infinite discontinuity at 0 and L, that has got to be compensated for by an infinite discontinuity in phi double prime, otherwise the equation is not satisfied at the boundaries. After all, what is the meaning of a boundary condition anywhere in the natural sciences, anywhere in mathematics? You have something inside a region and you want that to apply at the boundary, but you have something else at the boundary, and the difference between the two you call 0, and that is called a boundary condition. That is the meaning of imposing a boundary condition. You have an equation and you have some situation obtaining at the boundary, You want the equation to be valid at the boundary, so the difference between the two you call it 0. That is what you mean by applying a boundary condition, and that is exactly what is going on here. This thing here has to compensate for this, because phi n itself is continuous and bounded, so it can't do anything. This guy is showing an infinite discontinuity at the boundaries, and that must be compensated for by this, and that is why the wave function looks like that. So the consequence of this is that this fellow is not equal to a sum of two delta functions. It is some exponentials, you have to put the 0 here, you have to put the L here, and then you get a function. That function will extend from p equal to minus infinity to p equal to plus infinity. After all, you are all familiar with the fact that if you take a very sharp pulse in time and you do Fourier analysis, it has a very broad frequency spectrum. In fact, if the pulse is compact in time, it is infinitely spread out in frequency, and conversely if it is a monochromatic wave, then it goes like this from minus infinity to infinity, so it is infinitely spread out. The more you try to press in one quadrature, the more the other one spreads out, and that is a basic fact of life, which in quantum mechanics is called the uncertainty principle, but it is actually there even in wave motion, except that in quantum mechanics you got a dimensional constant playing a role there, the Planck's constant. So this is equal to some function, this is a smooth function of p. It is an element of L2, there is no question about it, it is an element of L2 minus infinity, infinity, guaranteed to be that. And the outcome, the upshot of it is that you do not have two delta function peaks when you compute the momentum space wave function and you calculate mod phi n of p squared, the probability that the momentum is something or the other from minus infinity to infinity, you get a function which looks like this. It has peaks about these points, that is in a nod to the classical case when you have just two sharp values of momentum, but the momentum of the particle inside the box could actually have any value, it is spread out. You can compute its average value. What is the average value of the momentum given this as the probability density? 0. Why is that so? It is inside, it is not going anywhere. Had it been non-zero, it would be moving, it would be going out, right? It is not going anywhere, it is inside the box. So that average is 0. Is the mean square 0? No, eminently no, eminently no. So now our next task is to calculate what is the mean square, etc., etc. So let us compute these numbers. So what is x average in the nth eigenstate? Let me put an n here to show that it is in the energy eigenstate that I want to compute this number. What is this equal to? Remember our general formula for the expectation value of A, an operator A in any state whatsoever. So this was psi A psi divided by psi psi, that is our general formula. Now we have to apply that to the present situation here. This guy here is always normalized to unity, so we have set it equal to 1, all our eigenstates are normalized to unity. The numerator is what we have got to compute. Now it is time independent because you are in a stationary state, therefore it is time independent. The average value of any physical quantity in which is not explicitly time dependent is constant, is time independent in a stationary state. That is the whole reason for calling it a stationary state. Now what would this be? This is equal to, how should I write this in the position basis? What should I do? Insert complete sets of states, so insert a state here, insert a complete set of states here, and then what happens? So let us write this as psi x x and integrate over dx, that is this is unity, and then you have an a, and then you have an x prime si, and you have an integral dx prime. That is what psi a psi was equal to. What do you call this guy? This fellow is just the wave function, but I want it in the state phi n, the energy eigenstate. So do you agree that I can replace this by phi n of x prime? You agree I can do that? Agree? Okay. What about this? It is phi n star of x. But I still have two integrals to do, and I want to look at the position eigenstates. So I want to look at x in the nth eigenstate is equal to this, and this is x operator. X operator acting on x gives you what? Just the number x. So this gives me just the number x, and then I have an x with x prime. But what is this? It is a delta function because it is an orthonormal basis. So this becomes a delta of x minus x prime, and then I can do the x prime integral. So I get rid of the x prime integral and I get x, this goes away, and all that happens is that you have a phi n of x. That is the formula you write down in the elementary treatments, psi star operator psi as a function of x, but it really came from this matrix element that I wrote by inserting complete sets of states and so on. Now these are all numbers, so it does not matter where I keep the x and move it around, it simply does not matter. So this guy here becomes equal to 0 to L because phi vanishes outside the box, otherwise it is minus infinity to infinity, you really must keep that, but this wave function vanishes outside. So it is dx 2 over L sine squared n pi x over L, and that is a trivial integral to do, multiplied by x, this guy here. So do it by parts or something like that, it is a trivial integral to do. What is x squared? What is x squared average equal to? All this would go through except the x would be replaced by x squared, and that is also a trivial integral to do, integrate by parts twice. So once you do that, I want you to work this out, compute delta x, this is the uncertainty, this is the standard deviation in the position. So you should compute this number, take x squared average minus x average squared, and then take the square root of the whole thing. That is guaranteed to be some non-negative number, some positive number. What about the momentum? What is this equal to? What would this be? Well, exactly the same argument would go through, except that you would have the momentum operator acting on this wave function here. And what is the momentum operator acting on the wave function? Minus I h cross d over dx phi n of x. Okay. What is this equal to? Oh, this is a sine, so this is some root 2 over L sine n pi x over L. What you get here? Cosine. And what is the product? The 0, it integrates to 0 because the momentum on the average does not do anything, it is 0. So this is 0. So this guy here, this is equal to x squared n minus, compute that number, and then delta p n equal to square root of p squared n minus p average n squared, and we just discovered this is 0 in this problem. What is p squared average? What is p squared average? Is it this squared? No, not true. The operator acts twice, so it is really d2 over dx2 pi n of x, and that is certainly not 0. That is certainly not 0. What is this integral equal to? I have to differentiate this, of course. This gives you again, this is sin n pi x over L, and if I differentiate once you get a cosine, if I differentiate a second time I get a minus sign, and then this already gave me a minus sign here, so these two guys cancel out, you get some mess of a number. Could we write this down? Yeah, but can we write it down even without looking at mean squared value of sine and so on? Yeah, it is just the energy, it is just the energy, right, because the energy is just kinetic. So you know the expectation value of the energy, therefore you can actually write this down. So it is certainly true that En is equal to n squared pi squared h cross squared over 2m, but that is also equal to p squared, isn't it? There is no potential energy in this problem. So you can actually write expectation Pn squared directly by multiplying 2m, you do not have to do the integral. But you got to be very careful when you say the energy is just kinetic energy, that is not true, that is not true. There is a potential outside which is infinite, energy inside which is 0, but it so happens that this integral is contributed to only by what is inside. Therefore it so happens that you could write down, once you know En, you also can write down p squared average. But already we saw with our lesson with the momentum wave function that you got to be damn careful, got to be very careful. So this is some number, hence compute this. And what are you guaranteed that this number should be greater than h cross over 2? Yeah. In fact you should see, you should work this out, it becomes larger and larger as n increases, and you will discover that it is dependent on n. The smallest value is for n equal to 1 in the ground state, and even there it is bigger than h cross over 2. So the ground state of this problem is not a minimum uncertainty state. Whenever this uncertainty bound is saturated, so delta p delta x is exactly equal to h cross over 2, I would call that a minimum uncertainty state, that is the least you could have. This is not a minimum uncertainty state, this problem does not have a minimum uncertainty state at all, okay, none of the eigenstates. So this is the way you compute the uncertainties in the problem, okay. And that more or less tells us everything we need to know about the particle in a one dimensional box. There are certain other aspects which we should ask, which we will talk about a little later, but again I want to ask, are the energy levels degenerate or not? No, in this problem they are not, they surely are not. Now as an exercise I would like you to do the following one dimensional problem. Imagine this particle is not inside a one dimensional box, but is living on a one dimensional circle, on a ring. So let us suppose it is living on a ring of size L, circumference L. So this is the point 0 and L. So a circle of circumference capital L. just to be able to compare with what happens in a box of length L. Exactly the same problem as before, no potential energy, no question of any potential at all in this case, it is just kinetic energy, H is p squared over 2m. Truly H is p squared over 2m. Therefore, would you or would you not expect the energy eigenstates, the Hamiltonian's eigenstates to be the same as the eigenstates of the momentum? Yes, in this problem you would. In this problem you would expect that every energy eigenstate is also a momentum eigenstate. What boundary condition would you put here? After all, the equation is exactly the same as before, you would solve exactly the same equation as before, but what boundary condition would you put? Phi of 0 is, so I would say here phi n of 0 is that a boundary condition? This is actually more than a boundary condition, because this is true at every x. In fact, what you are saying is and that is true everywhere, you are saying the wave function here is the same as the wave function there, and therefore it is equal to phi n of x plus 2l, x plus 3l, or x minus l, x minus 2l, and so on. These are called periodic boundary conditions. It is really not a boundary condition, they are periodic conditions, and the effect of this is that, please notice, when I say the function here is equal to the function at x plus l, it means every derivative of the function here is every derivative of the function there. So really it is an infinite set of conditions, the functions must match, the slopes must match, the curvatures must match, all derivatives must match. So really imposing a thing like this is like putting an infinite number of conditions, putting it everywhere. So this is very strong and it is sufficient, this condition is sufficient to find the unique solution here. I would like you to try to find the solution. What do you think the wave function is going to look like in this case? Do you think it is just going to be a sine n pi x over L? What should it be? Will it just be an exponential? Will it be, pardon me? It will be a superposition, but will it be a finite superposition? Remember, you need to satisfy this condition. So it will end up with a fairly complicated superposition, it is not a trivial superposition at all, but the energies, the energy levels would turn out to be exactly the same as what is there. If I have chosen my L such that it is the total length, it will still be h cross squared n squared pi squared over 2ml squared. Would they be degenerate? They are doubly degenerate. In this problem they are doubly degenerate, because one of them would correspond to momentum in this direction and the other would correspond to momentum in that direction. So these energy levels are doubly degenerate. Now very often in textbooks you would see the statement that in one dimensional problems you do not have degeneracy. This is true provided the underlying space is simply connected, a circle is not simply connected. So topology plays a role here, and in this problem definitely there is double degeneracy even in one dimension. So that is something to watch out for. We will try to come back and give this as an exercise to work out fully what the wave function looks like for a particle moving in a circle. This is crucial because these are the kinds of problems which one would encounter in applications. Now having made a few brief remarks about one dimension, we will take up 2 dimensions, I will do the rest of it tomorrow, but what would happen, yeah.
Why do you say a circle is not simply connected? What do you mean by this?
I mentioned this in the earlier course, if you recall, in the classical physics course. A closed loop on this space cannot be shrunk, all closed loops cannot be shrunk to a point without leaving the space. So it is actually infinitely connected. It is like taking the problem of putting a rubber band on a cycle wheel rim. You can encircle it completely once or twice or thrice or -1, -2, -3, an infinite number of different ways, distinct ways of encircling, of mapping. So in that technical sense it is not a simply connected space, but physically the circle's boundary conditions, the periodicity is such that there is truly no potential. The Hamiltonian does commute with the potential with the momentum in this problem, and energy eigenstates are momentum eigenstates in this problem. The consequence of it is that you do not have to solve the Schrodinger equation. You can solve the one dimensional equation, the momentum eigenfunction equation. You could solve the equation P on wave function equal to number times wave function, that is the first derivative equation, and superpose all possible solutions. They are guaranteed then to give you simultaneous eigenstates of position of momentum as well as the total energy. Okay. So we will return to that, but now we could do what we did for one dimension in a two dimensional box. Well, let us try that, the quickest of all. So now I have a wave function inside a square box in the x direction and in the y direction 0 to L. As usual I say the wave function is identically 0 outside and non-zero inside, and I can now separate the Schrodinger equation in Cartesian coordinates, and what would the solutions look like in this case? Phi would be described, so we go through this painful process of doing this, but let us suppose that you have two quantum numbers now, n1 and n2, because you got 2 degrees of freedom. So phi would be labeled by two quantum numbers n1 n2, and it would be a function of x comma y, and this is square root of 2 over L in each of the directions. So this is sine n1 by x over L. And what would be the energies be? E is now a function of n1 n2. Go to h cross squared pi squared over 2m L squared times of course n1 squared plus n2 squared. Those would be the wave functions. There is Cartesian symmetry between the interchange of x and y, so they look exactly the same. Okay. Are these energy levels degenerate? Yes, yes. Is the ground state degenerate? No, the ground state is not degenerate, it is unique. Agreed? Agreed? You can't put either n1 or n2 0, because then there is no wave function at all. So there is definitely the ground state, the lowest energy state, and E 1 comma 1 equal to something or the other, that is the ground state. Is the first excited state degenerate? Yeah, could be either n1 is 1 and n2 is 2 or vice versa, so it is doubly degenerate. There is a degeneracy in this. What about the second excited state? Two 2. How about 1 3? Which is bigger? Well, now you have to see, is 1 squared plus 3 squared bigger, or is it 2 squared plus 2 squared bigger? 1 squared plus 3 squared is 1 plus 9 is 10, 2 squared plus 2 squared just gives you 8. So clearly that is a lower energy level, and so on and so on. So the interesting thing is, of course you can do this numerology in the beginning, but the interesting thing to ask is, how does the degeneracy increase as n increases? As n1 n2 they all become very very large, how does it increase? And we will see what relation that has to do with density of states in 2 dimensions. What about 3 dimensions? What would happen? Same thing. Suppose the box were a rectangular box, what would happen? Suppose it were L1 and L2, then what would happen? Well, it would be the same as before, except this one is L1 L2, Are these degenerate? Depends on what? Depends on L1 over L2. So we are back to this thing about frequencies of two harmonic oscillators at right angles, similar kind of thing. So it depends on whether that guy is rational or irrational, on the geometry of the box. It clearly depends on that, and this you know from the drum. I mean, once you have the sides which are incommensurate, you have all kinds of modes possible, pure harmonics, but if they are not, then of course you have degeneracies and so on. So the same thing goes here, and you can play this game, you can do higher, you can do tetrahedral box, spherical box, all sorts of boxes. They are of academic interest, except that with the advent of nanotechnology and nanoparticles, it has become crucial now, because you can actually produce boxes, metallic particles which are confined to boxes of particular geometrical shapes. So it now becomes actually relevant to ask, what do the energy levels look like in different shaped boxes, very small boxes, and how do they get quantized. So that is an interesting problem to look at. What I am going to do next is to take off from this problem and introduce a potential and show you how, if you relax this condition of an infinitely rigid wall, then you start getting a spillover of the wave function outside. So we will talk about that tomorrow.